Okay, this is lesson 18, applications of the Pythagorean Theorem. We are going to continue looking at problems. There is no new information. Well, there might be a little bit of new information in this lesson and some techniques maybe that you haven't thought of. But for the most part, I would invite you to look over the problems and see how far you can get with some of these before you watch my solutions on the video, which I will provide. But yeah, so go ahead and just look through this lesson and work out the problems you can work out. Some of them have multiple steps, so and the big hint is in the title that the Pythagorean theorem is going to be used throughout, but that's not all. There's other things that you know about these geometric figures and drawings that you can bring to these problems. So I encourage you to persevere and work hard, and then come back and check your answers on these problems. Okay, so exercise 1 provides us with a right triangle, and only one dimension is given. Okay, so obviously we're going to need more information to determine any more information about this triangle. So let's read what the problem has for us. The area of the right triangle shown below is 26 and 46/100 inches squared. What is the perimeter of the right triangle? Round your answer to the tenths place. So in order to find the perimeter, we obviously need the lengths of all three sides. So this triangle, this right triangle, has two legs. So we'll call the first one A, the second one B, the other leg B, and then the hypotenuse we'll call C. So we can't really use the Pythagorean theorem yet because we need at least two sides or another relationship, but we've been given the area. So we know that the area of a triangle, is equal to 1/2 the base times the height. So because it's half of a quadrilateral, which would just be base times height, we know that it's 1/2 base times height. So our area, we know, so we can put it in this equation. We're going to plug in this value for area. So that would be 26 and 46/100, and I'm going to leave off the units for now, is equal to, and now I'm going to plug in the base and the height. So for this triangle, we can go ahead and use this for the base and this for the height. Because it's a right triangle, this is the perpendicular height, so base times height. So we've got 1/2. The base, which we know, is 6.3. And the height, which we don't know, but we're calling length B. So that's B. So we're going to solve for B this way. So I'm going to start by multiplying both sides by 2 to get rid of that 1/2. So I'm going to multiply by 2 and multiply by 2. Because what I want to do right now is solve for B. And so we're going to get, on this side, we're going to have 6.3 times B, because the 2 times the 1/2 equals 1. And then 2 times 26 and 46/100 is 52 and 92/100. Just multiplying 2 times that. A side note, and I know you've already done some of these problems now, go ahead and use a calculator, but which I'm doing, but notice I'm showing all my work. I'm showing my calculations, not just punching them into my calculator, because you know what happens when you do that is you end up with the wrong answer and you don't know where you went wrong. You don't know if you made a small error or if, something went really wrong. So now I'm going to divide both sides by 6.3, and this comes out to 8.4 for the second side of my triangle. So now I know that B is 8.4. So now I can use the Pythagorean theorem to find my last length. Because remember, my goal ultimately is to find the perimeter. So I need to find the hypotenuse now. So now I've got the Pythagorean relationship that I can work on. I'm going to use a different color. So I've got a squared plus b squared is equal to c squared. I'm probably going to run out of room here. But a squared would be 6.3 squared. And then we know now that b is 8.4. And I want to square that. And that when I add those together, I get c squared. So taking 6.3 squared and 8.4 squared, I'm going to get 39. This is 39.69. This here, 8.4 squared, 70.46. That's all equal to c squared. So I've got 110 and 25 hundredths is equal to c squared. Now I can take the square root of both sides, and get the value for c. So c is the square root of 110.25, and I want to find, I'm rounding to the tenths place, so I need to get this accurate to the tenths place. And it turns out that that number is actually 10.5 squared. So I've got 10.5 inches here, add some units here, 8.4 inches here. So now I can find the perimeter. So the perimeter is equal to 6.3 plus 8.4 plus 10.5. And add all those together, and I get 25.2 inches for my perimeter. Okay, so that required the Pythagorean theorem, but we also had to know about area formula for the triangle as well. Okay, problem 2 uses this diagram, which is, I'm glad they told us it was a soccer goal because it's kind of hard maybe to visualize this drawing, but hopefully you could visualize it. We're being asked to determine the length of the bar that would be needed to provide structure to the goal. So that's this bar right here, and there's a second one over here. And so it's labeled length C. So we need to kind of see where is this right triangle here. So because our right angle is here, these are legs. So even though this may not look like a right angle from the perspective, it's labeled like one, so it is. So the legs come off the right angle, and the side opposite it is the hypotenuse. So to determine the length of the bar, we can use the Pythagorean theorem. So we would have 8 squared plus 3 squared is equal to c squared. And so let me flip this around. So c squared is equal to 64 plus 9. So c squared is 73. And so c is equal to the square root of 73. So we know that that's going to be between 8 and 9, because 73 is between 64 and 81. So that's a good first guess. And so either by using approximation techniques that we learned earlier, or using your calculator, C is going to round to 8.5 feet. So C is approximately 8.5 feet. And so we're done with part B. How much netting in square feet is needed to cover the entire goal? So we've got this 10 foot, and then we know this is 8.5 feet, and again 10 and 8.5. So we can find the area. So we're looking for area. So we want the area that covers this parallelogram back here, and then the area of these two triangles. So the area of the triangle is going to be 1/2. Each triangle is 1/2 times 8 times 3. So that area is 1/2 times 8 is 4, times 3 is 12, and that's going to be 12 square feet. It's feet times feet. So we have 2 of those, and then the area of the rectangle on the back, we're going to call it, is base times height. So it's going to be 10 feet times 8.5 feet. So for that, we're going to have 85 feet squared. And so I don't have anywhere to write the total, but the total is going to be, let's just get a new sheet here. You can probably keep writing on yours. So we've got the total area is going to be 2 times 12 square feet plus 85 square feet. So this is going to be 24 plus 85 square feet. So we'd have 109 square feet of netting. Okay, so we're on 3. This has to do with TV ratios. So the typical ratio of length to width that is used to produce televisions is 4:3, length to width. Okay, and just so you know, TVs are sold by their diagonal measure. So if you get a 52-inch TV, that means it's 52 inches from corner to corner. Okay, so it's not the length or the width. A TV with those exact measurements would be quite small. Well, we haven't been given units, but whatever. So generally, the size of the television is enlarged by multiplying each number in the ratio by some factor of x. For example, a reasonably sized television might have dimensions 4 times 5 by 3 times 5, or 20 by 15, where the original ratio 4:3 was enlarged by a scale factor of 5. The size of the television is described in inches, such as a 60-inch TV, for example. That measurement actually refers to the diagonal length of the TV, so that's what we were talking about, from corner to corner. What measurement would be applied to a television that was produced using the ratio of 4 times 5 to 3 times 5? Okay. So this is the situation where the length would be 20 and the height here would be 15. So that would be my TV. And so what I want to know is what measurement am I going to give to customers to tell them how big the TV is. So it's this measurement here. So we can use the Pythagorean Theorem. C squared is 20 squared plus 15 squared. And that's 400 plus 225. So C squared is equal to 625. And so I can take the square root of both sides. And square root of C squared is C. And square root of 625 is actually 25. And so have we been given a unit? Inches. Okay, so that would be 25 inches, and that would be a 25-inch TV. So we'd call this a 25-inch TV here. Okay, let's go on with this. So a 42-inch TV was just given to your family. What are the length and width measurements? Okay, interesting. So what do I know now? I know the hypotenuse here. I know 42 inches right there. I don't know A and B. But I do know a relationship between A and B. And I know that the ratio between A and B is, well, between B and A is 4 to 3 or 3 to 4, depending on how you say it. So it's 4, the ratio is 4 to 3. So that means that there's some number, x, that I can multiply by 4 and by 3 and keep that ratio. So I could call one side 4x. We'll call this 4x. And we can call this side 3x. Okay, and then once I know x, then it becomes just like this problem here. I could solve for it. Okay, so we can use we only have one variable, so we'll be able to solve it. So this is going to be, let's change colors here. So we're going to have 4x squared. Now notice I use parentheses because it's 4x times 4x for that side length, plus 3x squared is equal to 42 squared. So 4x times 4x is 16x squared. 3x times 3x is 9x squared. And 42 squared is 1,764. Okay, notice even though I'm using a calculator, I'm writing everything out that I do. Okay, so 16x squared plus 9x squared is 25x squared. I'm going to get some equation solving practice here. Divide both of these sides by 25, and I get x squared is equal to this quotient, and I'm going to go ahead and just write out the answer since is 70 and 56 hundredths. So I've got x squared there. So I would like to take the square root of both sides now. And so I can see that x is going to equal the square root. Sorry, I'm writing all over the page here. X is equal to the square root of 70.56. So x is approximately, putting that in my calculator, 8.4. Okay, but that's not that's not the dimension, that's just x, right? So the dimensions we get are 4 times 8.4, which would be 30, let's see, what would that be? 33.6, and 3 times 8.4, which would equal 25.2. Okay, so these are the length and width of my, that one goes there and that one goes there, of my TV. So that's the length and width. And part B says to check out those dimensions using the Pythagorean theorem to make sure that they're correct. So to do that, we would go 33.6 squared plus 25.2 squared, and ask ourselves, is that 42 squared? And again, you're using a calculator here, but we're writing everything out. 1128 and 96 hundredths plus 635 400ths, and then this is of course 1764. So yeah, it looks like it is checking out exactly here. We get 1764 on both sides. Okay. So that might have been kind of a new technique to know that when numbers are in a ratio of 4 to 3, then we can write them as 4 times some number and 3 times some number. And those numbers there will be in the same ratio of 4 to 3, because the x is just a common factor there. So that helped us to be able to solve for the length and width there. Okay, the table that your TV currently rests on is 30 inches in length. Will the new TV fit on the table? Okay, so after doing all that work, this answer is pretty simple. It said no, because the width of our TV is 33.6 inches. So unless you want your TV hanging off the side, which could be fine, it's not going to fit. Okay, number 4. This is going to go back to the distance formula. And so the first two that we have here, we're given 2 points. And you could go get some graph paper and plot those points and find the legs of the triangle, because remember, we're going to have these 2 points and we're going to draw a right triangle connecting them and use the Pythagorean theorem. These distances, the legs, will be along grid lines, so they'll be easy to determine, and then we can use the Pythagorean theorem to find the length there. Okay, so I'm going to do it without using the graph paper, because I know that the distance, let's see, I'll use my pointer, that this distance here is going to be the difference in the y-coordinates. This distance here is the difference in the x-coordinates. Okay, so A will be 4 minus -2, which is equal to 6. And if you get a negative number for these, just use the positive, because it just means you subtracted the wrong way. So this is 7 minus -3, and that's going to be 10. Okay, and we don't need to know, like, we're not doing slope, so we don't need to know exactly what direction these are going. It's just distances, so we can use the positive. All right, so we've got 6 and 10 for the legs of our triangle. And so what we want to do now is use the Pythagorean theorem. So 6 and 10. So we've got c squared is equal to 6 squared plus 10 squared. And so that's 136. So c squared is equal to the square root of 136. That square root is pretty close to 12 because 12 squared is 144, but it's less than 12 and greater than 11. And putting this into your calculator to the tenths place, we're going to get 11.7. Or actually it's going to round to 11.6. Okay, so 11.6 for the distance there. Okay, and then this one, let's look at the difference in the y coordinates would be 2 minus 6. So that would be -4, but I'm going to just use absolute value here because once again, I only care about the positive distance. I don't care whether it's here or here, just the positive distance. Okay, so that would be 4. And then the other one here, the difference in the x coordinates would be -5 minus 3. And I'll take the absolute value of that. -5 minus 3 is 8, -8. So our distance here is 8. So we've got 8 and 4. And you can graph it to see what's happening there with the negative numbers. If you want to graph those 2 points, that'd be fine. But c squared is equal to the sum of the legs squared. So I've got c squared is 16 plus 64. C squared is equal to 80. So c is equal to the square root of 80. That's really close to 9. And if you put this one in your calculator, that c is going to be approximately 8.9 units. 8.9 units. Okay. All right, so this challenge problem I'm going to do on the next page. So what the challenge problem is asking us to do is to use, instead of not x1, x2, what am I doing? x1, y1. So what we're doing is we're writing general points, any point, and x2, y2. Okay, so to find, and then to use the Pythagorean theorem to find the distance between, so we've got x1, y1, x2, y2. What is the distance between those 2 points? Explain your answer. Okay, obviously we're not going to get a number for this, but we are going to get an expression. Okay, so let's let c be the distance between these 2 points. Between the points. So c is the distance between the points. So, so we've got 2 points here. C is this distance here. So what I need to know is, what are these distances? So we've got kind of x1, y1, and x2, x2, y2. Those are the coordinates of those 2 points. and we're asked to find the distance between them, and we're going to call it C. So this is kind of challenging, and in a standard algebra course, you'd probably just be given this formula and maybe asked to memorize it. But you don't want to memorize it because you can derive it. And if you're like me, you don't like to memorize anything. So what is this distance here? Well, if this y coordinate is y1, then so is this over here. This y coordinate's y1 and y2. So I can say, y2 minus y1. So I'm going to write that. That's the y2 minus y1 is that coordinate. And then over here, this is x2 and this is x1. So I've got x2 minus x1 would be that. And we're just going to go absolute value because I don't really know, I don't really know where these points are, but they're just positive distances, whatever they are. I hope that makes sense. And the thing is we're going to square these numbers anyway, so if they're negative, they're going to end up positive. So I'm going to say that y2 minus y1 squared plus x2 minus x1 squared. So just what we did in the other problems, we took the difference in the x-coordinates, that was the horizontal distance. The difference in the y-coordinates was the vertical distance. We squared those and we said that equals c squared. All right, so now what we want to do is we want to take the square root of both sides. So we're going to take the square root of this whole thing and say that's equal to the square root of that. So we end up with something that looks like this. Square root of c squared is c is equal to the square root of y2 minus y1 squared plus x2 minus x1 squared, and the square root of that whole thing. So this is, you'll see this referred to as the distance formula. And I can just put in the coordinates of my points. x1, y1, x2, y2, and there's my formula. So this might look slightly different. It doesn't matter. The subscripts could go the other way. It could be y1 minus y2, x1 minus x2. This term should probably be over here, but it's all the same. It's all going to come out the same. I could write it, this is the way you might see it. X1 minus x2 squared plus y1 minus y2 squared, but they're exactly the same because I'm squaring the distance between the coordinates, x and y, adding them together and taking the square root of the whole thing. That's exactly what we did in both of these problems. So the square root of 136. Oh, I just saw a mistake there. C, not c squared. C is equal to that. I did that. Yeah. Sorry about that. Hopefully you caught that. So anyway, that's called the distance formula, and it would definitely not be something that you would want to memorize, I don't think, unless it had a lot of meaning to you. You would want to just figure it out when you need it. Okay? So that's kind of the challenge problem there. So I don't know if any of you were able to get that on your own, but hopefully you understood the explanation there. Okay, one more application before you work on your problem set. What length of ladder would be needed to reach a height of 7 feet along the wall when the base of the ladder is 4 feet from the wall? Round your answer to the tenths place. I think we did problems similar to this back in module 2 or 3 when we were doing Pythagorean Theorem back there. So they've done the hard part here, which is to label the diagram for you. So here's the ladder leaning up against the wall. We need to reach 7 feet. So we want to know what is the length of, how long do we need this ladder to be able to do that? So c squared is 7 squared plus 4 squared. So c squared is 49 plus 16, which is equal to 65. C squared is 65, so c is equal to the square root of 65, which is really close to 8, right? Because 8 times 8 is 64. So if I approximate this with a decimal, it's going to round to 8.1, and these are feet. So my ladder needs to be at least 8.1 feet to reach up 7 feet on the wall when placed 4 feet out. Okay, so a couple examples in this lesson were sort of three-dimensional examples, like this ladder one was a three-dimensional example, whereas many of the problems we'd been doing with the Pythagorean theorem were two-dimensional. Okay, so like let's look at our TV example was really two-dimensional, but we had another problem back here that was three-dimensional, like this one. Here's kind of a three-dimensional soccer goal here that we were still able to use the Pythagorean theorem on. So in the next couple lessons, we're going to be continuing to use the Pythagorean theorem in a three-dimensional context. So go ahead and work on this problem set, and we will, in the last couple lessons, we're almost done. We'll be on lesson 19. We're only going to 22, so we're getting close. But we're going to look at some three-dimensional geometry, but still using the Pythagorean theorem. So good luck on that problem set, and we will see you back here for 19.